Hi, welcome to Massive Open Online Course MAT 522. This is Chapter 5, Applications of Second-Order Linear Differential Equations. In this chapter, we will be learning two different applications, how to model and solve them. This first video considers spring mass system. Here, consider a simple spring mass system with a spring suspended vertically from a rigid support and a mass attached to it. Now, this spring mass system is governed by two basic physics laws, namely Hooke's law and Newton's second law. For the first Hooke's law, the spring itself exerts a restoring force opposite to the direction of the extension and proportional to the amount of the extension S. Simply stated, F equals to Ks, where K is a constant of proportionality. Here we call it spring constant. For the second, Newton's second law. This Newton's second law discusses the net force of the restoring force and the weight. If we consider figure B, here, after a mass is attached to a spring, it stretches the spring by an amount of S here and attains an equilibrium position in which now the weight W is balanced by the restoring force F. That is, mg equals to Ks or mg minus Ks equals to 0. Furthermore, if the mass is further extended or displaced by an amount of x from equilibrium position, as in the figure C, then the restoring force becomes K multiplied x plus S. This gives us the first type of the spring mass system, the free undamped motion. If we assume that there is no external retarding forces acting on the system, and that the mass oscillates free of other external forces, then we say that the spring is in free motion. This gives us the first equation here, such that m d square x over dt square equals to negative k multiply x plus s plus mg. If we expand this part, then we obtain negative kx minus Ks plus mg. By the net force in between weight and the restoring force that we discussed just now, we notice that this term eventually becomes 0 because mg minus Ks equals to 0. Then overall, this gives us a simplified version of negative Kx on the right. Hence, we have the first second-order linear ODE for the free undamped motion, mx double prime plus kx equals to 0. However, we know that in reality, free motion is kinda not realistic because somehow there will be at least a resisting force due to surrounding medium occurred. So here, we consider the damping forces act on a body that is proportional to a power of the instantaneous velocity. So here, we consider the damping forces with damping coefficient beta. And the first equation that we have seen just now can be further updating into second equation, in which now we take account the damping forces minus beta dx over dt. This gives us the second order linear ODE of mx double prime plus beta x prime plus kx equals to 0. That is the free damped motion of a spring mass system. Furthermore, if we now take into consideration external forces act on it, then we can further updating the equation 2 we have just now into the third one, the final one, by adding on the external forces F in terms of T. This gives us the next second order linear ODE mx double prime plus beta x prime plus kx equals to F in terms of T, that is the driven motion of a spring mass system. Combining all this concept, overall, we have three different categories, three different models, either free undamped motion, free damped motion, or driven motion of a system of a simple spring mass. Now, before we move further, there are some important and useful notes, formulas, and unit conversions that you have to take note when dealing with spring mass system problem. Again, Newton's second law tells us the net force in between the restoring force F and the weight W. So here, W equals to mg, m represents the mass, g represents the gravitational force. Here, if the unit measurement of the weight is in terms of Newton, then the associated gravitational force G will be 9.8. On the other hand, if we consider power force in the unit measurement of weight, then the associated gravitational force G will be 32. Hooke's law is given by F equals to Kx, where K is the spring constant, X is the stretch. Next, if the length is measured in the unit of feet and inches, take note that 1 foot is equals to 12 inches. Last but not least, consider the direction of the motion. If the direction pointing upward, then it has negative values. Whereas, if the direction is pointing downward, then it will be positive. If you are ready, then we can look into the first example in constructing a second-order linear differential equation. A mass weighing 2 pounds stretch a spring by 6 inches. At time t equals to 0, the mass is released from a point 8 inches below the equilibrium position with an upward velocity of 4/3 feet per second. So here, the first information that we have is the weight 2. Therefore, W equals to mg, which means 2 equals to m multiplied by 32. Because the unit measurement is in pound, therefore the associated gravitational force G will be 32. This gives us the mass m equals to 2/32, or simplified into 1/16. Next, the restoring force F equals to Kx, in which the spring constant K equals to F/x. We know that the force F should be the same as the weight, therefore 2 over the stretch. Take note that the stretch is given in inches, 6 inches, and we know that 1 foot is equals to 12 inches, and therefore, by simply converting 6 inches, we have 6 inches equals to 6/12. This is 1/2 feet. So substituting the x by 1/2, we have the spring constant that is equals to 4. Having m the mass and the spring constant k, observe that in this question, no damping forces are exerted into it. Therefore, this model will be a free undamped motion model, mx double prime plus kx equals to 0, and that we have 1/16x double prime plus 4x equals to 0. If you prefer, you can simplify this model further into x double prime plus 64x equals to 0. This solves the first statement in the problem. Now, observe further, there are some initial conditions provided in this problem. That is, First, when t equals to 0, the mass is released from a point 8 inches below. We just learned that below has the direction of positive motion. And again, 8 inches, if we convert it into feet, this gives us 8/12. That is 2/3 feet. Therefore, the first initial condition will be x of 0 equals to positive 2/3. Second initial condition, upward velocity of 4/3 feet per second. Again, the upward direction has negative sign. Therefore, the velocity gives us the second initial condition, x prime of 0 equals to negative 4/3. Having the model and the corresponding two initial conditions, this gives us the complete model for this example number 1. Now, let's consider example number 2 to further familiarize ourselves with the construction. Here, a 2 kg steel ball is attached to a spring and is stretched by 4.9 meters, attaining an equilibrium position. Now, the steel ball is set into motion from rest at 1 meter below equilibrium position. Assuming there exists air resistance of 9 times the instantaneous velocity, now construct a second-order linear differential equation to represent the scenario described above. Here, the mass is given immediately, m equals to 2 kg. So we don't have any problem in finding the m. Next, the spring is stretched by 4.9 meters. Therefore, to find out what is the spring constant, we use the formula from the Hooke's law, F equals to kx, again, in which k equals to F divided by x. Here, we have the information about x, which is 4.9. What about the value of F? Again, based on the Newton's second law, net force binds the relation between weight and restoring force F. Therefore, we can proceed to find the weight W first, which is equals to mg. This is just 2 multiplied by 9.8. Again, kg is associated with the gravitational force of 9.8. This gives us 19.6. So the weight W will be the same as the restoring force F. Here, 19.6 divided by 4.9 gives us spring constant 4. Now, we also notice that there are air resistance of 9 times the instantaneous velocity provided. This indicated that the damping coefficient beta is equal to 9. That is, this spring mass system represented by a free damped motion. So substituting these three informations into the model, mx double prime plus beta x prime plus kx equals to 0, then it becomes 2x double prime plus 9x prime plus 4x equals to 0. Again, there are some informations about the initial conditions given. First, the steel ball is set into motion from rest. That is, the steel ball did not move at all at the beginning. This gives us x prime 0 equals to 0 for the velocity. In addition, 1 meter below equilibrium position. Again, downward direction is represented by positive sign. Therefore, x 0 equals to positive 1. Having these two additional initial conditions together with the second order linear differential equation, we have a complete model for this example number 2. Now that's it for the construction of the spring mass system into second order linear differential equation. We will learn how to solve in the next video. That's it. See you in the next.